Math 2414, Calculus 2. Calculus 1 review. Derivative rules part 2. In part 1, we reviewed 6 generic rules, and in the remaining parts, parts 2, 3, and I even have a part 4, we're going to be looking at specific functions. But I also summarized these generic rules over here using a slightly different notation. You probably remember from calculus that there are multiple ways to represent derivatives of a function. A common way is using the apostrophe or a prime, if you will, on function notation. Another way is to write d over dx in front of a function of x, saying I'm taking the derivative with respect to x. There are other ways that we will review as we run across them, but which one you choose to use really just depends on the situation. But I did summarize the first 6 rules over here using similar notation on the right, which is kind of funny because I'm using the ddx on the left with prime notation on the right, but hey, it's all good. All right, let's pick up with rule number 7. If f of x equals e to the x, then f prime of x is equal to. Really easy derivative rule, but I just want to remind you what e is. E is called the natural base, but it's actually the limit of something. It's the limit as n approaches infinity of 1 plus 1 over n to the n power. Or you could say the limit as n approaches 0 of 1 plus n to the 1 over n power. These are equivalent. I'm not going to bother proving that they're equivalent, but both of them give you the same value. If you wanted to estimate it, it's about 2.71828.1828459045. That's all of it that I know. You don't have to have it memorized, but to however many decimals that is, looks like that's 15 decimals, that's what it is. But it's a number that shows up in a lot of natural occurrences, hence the name natural base. But its derivative is easy, or rather I should say the derivative of e to the x is easy. The derivative of e to the x is e to the x. One of the easiest derivative rules ever. It's its own derivative. It's also its own antiderivative. Number 8, if f of x equals b to the x. This is like rule number 7, except instead of the specific base, it's a generic base. Now anytime you're talking about bases, at least if you want to stay away from complex numbers, we always require that the base be positive, but not equal to 1. The reason the base is not equal to 1 is because 1 to any power is equal to 1, and it's really a constant function, not an exponential function. But if you want to take the derivative of any number to the x power, as opposed to e to the x power, it's like the e rule, except you start with the natural log of the base. It's the natural log of the base times b to the x. So the exponential part stays the same, just like up here. You just have to compensate for the fact that the base is an e by multiplying by the natural log of the base. And by the way, rule number 7 is just a specific version of rule number 8, because if we let b equal e, we would get the natural log of e times e to the x, but the natural log of e is equal to 1. After all, that's how natural log is defined, as logarithm base e. If you need a review of logarithms, and by the way, if you need a review of anything from college algebra, I have a complete set of videos for college algebra taught at Tyler Junior College, and I'll be happy to share some links with you if you would like a review. So when I say things like, of course, natural log is just log base e, if you're like, wait, what? Message me, I'll link you up to the videos that review the algebra. But I have to assume that the algebra is there already. Number 9, if f of x equals the natural log of x, then f prime of x is equal to 1 over x. Pretty easy derivative. The derivative of natural log of something is 1 over the inside. And number 10, if f of x equals log base b of x, same restrictions on the base, positive but not equal to 1, then the derivative, now this is a rule that a lot of people don't remember because it's not used that terribly often. It's kind of like the derivative rule for natural log, it's 1 over x, but you'll notice I left a big old space in front. The relationship between these two derivative rules is like the relationship between these two derivative rules. When you're doing natural base or natural log, it's easy. But when you change the base, either exponentially or logarithmically, the rule stays the same. You just have to compensate for the fact that the base is an e by multiplying by the natural log of the base. But in this case, it's down here. It's actually not difficult to prove this rule from this rule if you have a couple of tools at your disposal. Actually, the only rule that we need is what's called the change of base property. So in terms of reviewing calculus, I'm done. I'm about to do a theoretical follow-up, so if you're okay with the rules and aren't interested in the theoretical follow-up, feel free to stop watching the video. I would watch it though, because I expect you to know algebra, and all I'm going to do is prove this using a little bit of algebra. In order to prove it, one way to figure out something new, this is a problem-solving skill that is very valuable. It's kind of obvious if you think about it. But one way to learn something new is to connect it to something that you already know. So let's assume that we already know the derivative of natural log of x is 1 over x, and we want to know what the derivative of this is. Well, we can use something in algebra called the change of base property for logarithms. If you're curious, I can link you to the video that introduces and reviews it. But the change of base property for logarithms basically says you can change the base to anything you want by simply writing a ratio of logs. In this case, we can write the natural log of x over the natural log of b by changing it from base b to base e. Again, if you would like a review of the change of base property for logarithms, message me and I'll link you to that video that I have. But if we do this, then we can do a little bit of algebraic smoke and mirrors by rewriting this as 1 over the natural log of b times the natural log of x. Now, we haven't taken any derivatives yet. We've just done some algebra to connect what we don't know to what we do know, or rather to connect what we don't know about to what we do know about, which is the derivative of natural log of x. So if we take the derivative, this is a constant times a function, and we already have a rule that says when you take the derivative of a constant times a function, leave the constant alone, take the derivative of the function. Well, 1 over natural log of b is a constant. The derivative of natural log of x is 1 over x, and if we multiply the fractions together, ta-da, we get the rule. Again, if you just know the rule, that's fine, but frankly, you're going to be a better mathematician, theoretical or applied, it doesn't matter, if you understand how to create new knowledge based on old knowledge. Because believe it or not, there's a lot of unfound knowledge out there. Maybe one of you will find something new, get rich, and remember me. All right, so there's those rules. In the next two, we're going to start looking at trigonometry.